Chen, thank you so much. During that whole introduction, I kept looking around to see who you might possibly be talking about. That was quite overwhelming. Thank you all so much for coming at such an incredibly busy time of the year and the semester. I am on sabbatical. I'm in Rome. What that means is that I'm hunched over a little teeny laptop instead of in front of the usual, kind of computer setup. And so I apologize in advance if the technology gets funky. Just flag me down if anything weird happens. Okay. So I want to start with a big question that we rarely stop to think about. Why do babies learn language? Not how do babies learn language. We think a lot about that. We talk about that all the time, but why do babies learn language? And in some sense, the answer seems really obvious. Babies learn language because they want to communicate with the people around them. They want love, they want stuff, all the things, and that makes perfect sense. But there's another kind of answer as well, and it's quite different. The other answer is that the computational properties of babies' brains are a really good match for the structure of language input. So to put it another way, and I've had people give me this answer when I say, why do you think babies learn language? Babies learn language because they just can't help it. This is kind of what our brains do. So how can we adjudicate amongst these possible driving forces in early language learning, which may well be working in tandem? In my presentation today, I'm going to use statistical learning as a lens through which to consider questions about why babies learn language. Statistical learning, which Chen kindly referred to in his introduction, refers to the ability to detect, track, and remember patterns of information, what things go together, which events predict which other events, and so on and so forth. So to make this a little bit more concrete, some of the earliest evidence for this sensitivity comes from studies with artificial languages, where with Dick Aslin and Alyssa Newport, we investigated how infants might track patterns like this. I'm going to assume people could hear that. Yes, good. Okay, fabulous. Um, in subsequent work, we broadened out the questions to include not just artificial languages, but real languages. This happens to be stimuli from an experiment done back in the early 2000s, but it's particularly germane to my current existence today.
Gusto i vicoli dentro casa ho coricato all'ombra del melo verde. Per ascoltare la fuga, quasi cadi sul melo e inciampi sulla via o sull'erba.
So when we expose infants to sequences like this, we discover that they are quite sensitive to patterns of which syllables predict one another in those sequences, figuring out something akin to where words begin and end. But it's not just language. Here's some other stimuli from another set of experiments that I did in grad school with Elizabeth Johnson, Dick Aslin, and Alyssa Newport. There was a weird echo there. My machine just said playing music question mark. Not so much. But anyway, the point is that infants are sensitive to statistical regularities, not just in speech, but in musical sequences, in visual spatial sequences, temporal visual sequences, so on and so forth. There is now, I would argue, a reasonable consensus that infants are sensitive to these sorts of patterns and regularities, though reasonable people would also disagree about the explanatory power of those abilities. But that's not actually what I want to talk about today. That's a different set of talks. Instead, what I want to do is to share some of the newer ways that our group has been thinking about statistical learning and come back to these why questions, not what or how questions. So, why do babies track statistical patterns in language input? Well, as novice learners, as people who know very little about the ambient auditory language around them or the visual language in the case of sign languages, infants are faced with input that is massively unpredictable and thus extremely difficult to encode and process. Just think about yourself on the bus with someone behind you speaking a language you don't know. It's really hard to hang your hat on anything that's going on. It's just, there's a lot of information there. As infants attempt to reduce the uncertainty in their environment, statistical regularities may be very helpful, helping them to encode and process all that input around them. So on that kind of view, Infant statistical learning, or statistical learning more generally, not just language, is essentially a byproduct of infants' attempt to process the environment. Put another way, with language, their goal, I would argue, is to process language, to encode language, not to track statistics. That's not the goal. Statistical information may help infants to encode the input more efficiently, facilitating downstream learning and processing. So, to the extent that that's the case, it reframes the empirical approach. It reframes the research question. Instead of asking which statistics do infants detect, the questions that I've become interested in concern how infants exploit statistical regularities in the service of real-time language relevant behaviors. Okay? Now, that all sounds great in principle, but to borrow the format of a popular meme, how it started, how it's going. So here's the good part. I no longer think, as I once did, that babies are passive sponges just soaking up statistical regularities. However, because of the past 5 years, because of COVID, recruitment challenges that all of our labs have been facing, our attempts to actually test this sort of hypothesis about statistical regularities affording language processing have been really slowed down. And so rather than having the body of work that I'd love to talk to you about today, I'm going to be presenting a mix of studies that are in progress, some pilot data, as well as some published work to kind of frame where I hope to be going with these ideas. So what I'll do in today's presentation is to examine the competing effects of, on the one hand, predictability. An efficient learner should really exploit predictability because it facilitates encoding, it facilitates real-time processing. On the other hand, an efficient learner should seek out uncertainty. It's not very useful to sort of stick with the stuff you know. You got to find the stuff you don't know. And statistical regularities may be very helpful for young learners as they try to discover what they don't know. So these may be complementary roles for statistical learning. Okay, so let's start by thinking about some of the ways in which statistical regularities make language more predictable. Of course, there's now massive amounts of work in machine learning and large language models that do this, but I'm going to take the baby's perspective. So, or maybe your perspective. Let's go back to you sitting on the bus. The person behind you is speaking Thai. You don't speak Thai. As you first start listening to them, it's just noise, right? I mean, you don't know where the words are. You don't know how they combine. You don't know what the words mean. You got nothing. You just got the sounds. Until you find the words, the structure is actually opaque for you. And we know from work done over the past few decades that statistical regularities can help babies find that signal. They can give babies a place to hang their hat, as it were, facilitating the encoding of next level units. So going, for example, from syllables to words, which is absolutely crucial for downstream learning. You can't learn the meanings of words or how they combine until you find the words. So to take that weird artificial language example from a few minutes ago, this is what we played for babies back in a long time ago, 25 years ago. This was the underlying structure of what we played for babies. So these syllable sequences do have structure. There are words. They're only words to me. I'm the only native speaker of this language, actually. But why does this matter? Well, if babies can go from this to this, now new levels of structure become apparent. So, for example, these word forms can help babies go to a new level of representation, actual words. And in fact, work done by Katie Graf-Estes in my lab when she was a graduate student demonstrated that infants, as they listen to these syllables, sequences, begin to extract units that can then be mapped to meanings. Infants are also able, once they find these word-like units, to figure out how they combine. So if we give babies a sequence of syllables that cohere into words, and the words are organized by a grammar, infants can go from that syllable level to the word level to finding the grammatical structure within a single set of input. There's this sort of process that mimics what Karmeloff-Smith described as representational redescription. That is what you've learned at time n at any given moment can afford new ways of processing the input at time n plus 1. And this is going to be really important as babies go through this cascade of language learning. So these statistical patterns can inform infants' expectations about word forms. So as I just mentioned, they help babies make predictions about which sound sequences are likely to have meanings attached to them, word tokens. They also provide generalizable information about the kinds of sounds that are likely to begin or end words, or which kinds of words are likely to have similar meanings. The broader point I want to make here is that all this work that babies are doing in the first year, picking up these patterns of sounds, actually really matters. It can affect their expectations as they start to build their vocabularies, with many implications for the roots of individual differences, the roots of atypical development, and so on and so forth. If you can't find the words, you're not going to find the meanings or the grammar. Now, moving beyond predictions about the structure of individual words, what about word combinations? Can babies predict upcoming words based on sequential statistics, which is at some level what a lot of computational models, including large language models, do? They're making predictions about what word comes next. Now, we know from a large, now quite large literature that adults, kids, and even toddlers engage in predictive language processing. So they are able to use cues in speech, many different kinds of cues in language, to generate expectations about what word is likely to occur next, or what kind of word is likely to come next. So to give you just a really classic example of this sort of predictive processing, we have the classic study by Altman and Comide, where when adults, and this has now been studied with toddlers and children as well, when they hear a sentence like ride the bike as opposed to find the bike, they will launch an eye movement earlier in the context of the semantically constraining verb ride, using that to make a prediction that bike is coming downstream. And so we know that there's all sorts of information that learners and processors are using to generate expectations about what words are going to come next. But can babies do this just based on sequential statistics? These sorts of effects of, say, semantic constraint obviously are correlated with statistical patterns, but they're not, but they don't tell us whether babies could do this without knowing anything about meaning. And this is important because statistical regularities, like this word is followed by this other word, are arguably easier to learn and learnable younger than the cues I had on the previous slide, morphosyntax, semantic constraint, etc. Indeed, given the limitations on infants' linguistic and world knowledge, their language processing may be especially impacted by bottom-up statistical patterns like lexical bigrams, that this word predicts this next word, just based on the numbers, not based on meaning. It could be really helpful for managing the deluge of language input that infants are confronted with. And if babies can do this, if they can use statistics of word sequences to make predictions, it could also be a mechanism whereby the quality and quantity of language input impact language development, because we know that predictive processing requires a lot of good data. So can babies do this? Well, back in 2016, Koenig and Mani wrote that there is, as far as we know, currently no direct experimental evidence available that unequivocally links the detection of sequential statistical regularities to mechanisms of predictive language processing. No. The answer is no, according to Koenig and Mani. And to date, we have some hints. One of my favorites is a paper by Abuzaya et al. That shows that for children, grade school age children, they make stronger predictions for what words will come after a verb like throw, based on the frequency of the objects that are paired with that. So that sort of hints that maybe sequential statistics might have a role. But we still don't know, to my knowledge, and folks should email me afterwards if there's stuff I don't know in the literature. So one of the studies that I'd hoped to be able to show you full data for today was designed to ask this exact question. So this is a study that we've been doing in our lab with my grad student Ellie Breitfeld and my postdoc Iran Chen. And I think we are literally 3 babies away from the full sample, but because it's pre-registered, I couldn't look. So I'm going to show you pilot data. So this study was designed to be a very simple way to ask whether babies, if we expose them to word pairs where we manipulate the statistics and there's no meaning cues to tell them what comes next, will babies make predictions? I guess technically they're toddlers, so 20 to 22-month old. Yeah, same point. So here's the design of the study. So babies are first exposed to word pairs like happy kitty and little fishy, where we always have a familiar target word like kitty or fishy, and we make sure babies know those words because we need a target for their predictive eye movements. And what we do during training, during exposure, is we manipulate the statistical relationship between the adjective and the noun. Some adjective noun pairs, like say happy kitty, are deterministic. Every time the baby hears happy, it's followed by kitty. Others are probabilistic. So little is followed by fishy half the time and by something else half the time. Here's the design of one condition of this experiment. So happy is always followed by kitty, pretty is always followed by doggy. Um, Little is followed by fishy half the time, and silly is followed by ducky half the time. These 4 bigrams are going to be the ones we're going to test. And of course, we counterbalance this so that for half of the babies, happy kitty is probabilistic. Okay, so that's the design. I'll walk you through. So babies get exposed to this structure. It's very, very simple. Deterministic pairs, probabilistic pairs. And then we use gaze contingent eye tracking to assess prediction. We want to see whether babies are better at predicting which word comes next when it's a high probability sequence. So how does this work? So after the training, babies will see a pair of objects here, like a doggy and a kitty. These were both from deterministic trials, from deterministic pairs. The objects are in grayscale. And then they're going to hear a predictor word like happy. And what we do is we wait until they look at the right answer. So when they look at kitty, so let's say, so kitty is the right answer. That's the sequence. Let's say they look at doggy first. Nothing happens. And then when they look at kitty, then they get to hear kitty. So it's a reaction time task. We want to see how quickly they get to the correct target. And when they get to the correct target, it lights up and they get to hear its label. So that's the reaction time we're interested in here. So let me just show you a little video of this task. Hopefully you can hear it. It's quite quiet, but you'll get the idea. For any videos I show you, right is left and left is right. So if the baby is looking this way, it's actually triggering the stimulus on the other side.
Happy kitty. Silly ducky. Pretty doggy.
Okay. So our hypothesis here was that if babies are sensitive to these statistics, the word pair statistics, then they should be faster to the target for the deterministic pairs because they're able to use that predictor word to guess what's coming next before it happens in a more efficient way than for the probabilistic pairs where there's still a correct answer, but it's less strongly probable. And these bigrams were equally frequent during training. And here's just this little bit of pilot data from 11 babies. And what you can see is that as a group, the babies are faster on the deterministic trials than on the probabilistic trials, consistent with the hypothesis that they are making predictions based on these sequential statistics of which words go next. However, we are waiting on that full data set. So we'll see what happens. If we do see this effect, then there's so many different kinds of questions we can ask about richer patterns and regularities than just this very deterministic versus quite probabilistic structure. Now, another way in which predictability can facilitate language learning is by guiding attention. So the next study I want to tell you about was done by Vidi Benitez when she was a postdoc in my lab. She's now an assistant professor at Arizona State. And Vidi and I spent a lot of time thinking about trade-offs between predictability and surprisal for infants. On the one hand, basically all of the cognitive and perceptual development literature tells us that surprisal is good. It draws attention. So, for example, one of my very favorite studies from the past decade was work by Amy Stahl and Lisa Feigenson showing that infants learn more about the sounds of objects when those objects do really weird things like hang in the air or go through barriers. And more generally, there's a lot of interest for a long time, going back to Jeff Elman's work, about ways in which prediction error, which is a form of surprisal, triggers learning and can help learning occur. So, on the one hand, surprisal seems to be a really beneficial thing. On the other hand, predictability also seems like a really good thing. When you're learning something within a predictable environment, you're less likely to be distracted by extraneous or irrelevant features of a learning moment. You can hone in on what actually matters. And so Vitti and Linda Smith had previously argued that this sort of predictability, at least in word learning contexts, can actually help scaffold infants' attention. So what Vitti and I decided to do was an experiment where we manipulated predictability and surprisal during word learning. Rather than doing something really dramatic like violating core knowledge, like objects hanging in the air and violating gravity, we decided to generate novel expectations in the lab. So this study had three parts. The first part, babies are going to get exposed to they're toddlers. Sorry, I get the word, I use them interchangeably. Um, I guess the International Society for Infant Studies says infants are up to 3 years, so we're okay. Um, Infants are exposed to a very predictable visual-spatial sequence that I'm going to show you in a moment. We then embedded word learning moments in the sequence. Some of words were trained in predicted locations, other words were trained in surprising locations. And then we test them to see whether they were better at learning one kind of word than the other. So here's what the exposure was like in this task. So um, just music is playing, weird objects from the noun database are popping up in a very predictable order. And pretty quickly, infants start to make anticipatory eye movements in this sort of clockwise direction. So they learn pretty quickly the structure of this exposure. Following that, infants are exposed to naming events. Some objects are labeled only in predicted locations, and some objects are labeled only in surprising locations. In this test, we again use gaze contingent eye tracking. You'll see that throughout this presentation. It's our current favorite thing because we wanted the labels to only occur once the infant fixated the object. And the infants might be slower to fixate the object if it occurs in an unexpected location. So objects are always labeled once the infant has fixated that object. So let me show you what that looks like. So this is a naming event in a predicted location.
It's a bossa.
Pretty exciting. Okay. And then here's a surprising location.
It's a tulver.
Shocking. Shocking, I know. Okay. We then tested babies on test items. There were either two events that were trained in surprising locations, or two objects that were trained in predicted locations using a looking while listening task, very standard task where babies hear an object label and we measure how quickly and accurately they shift their gaze to the target. And in brief, what we found is that predictable locations seem to facilitate word learning relative to surprising locations. This is actually a little bit counter to what we expected. We thought that the surprising locations might heighten infants' attention. But instead, what we found is that at least in this kind of situation, the sort of spatial consistency seemed to scaffold learning such that predictability helped to afford stronger word learning in this particular case than surprising locations. And so there probably are really interesting features of this task compared to something like the Stalin-Feigenson task that led predictability to be the dimension that enhanced learning. Okay. Speaking of predictability and uncertainty, I want to switch gears to talk more about uncertainty more generally and why it matters for learning, not just surprisal, but uncertainty. So I want to return to the big question that I started the talk with, which is why do babies learn language? Why do they learn anything to begin with? Um, and the field seems to be cohering around a strong interest in the argument that a major goal of learning, or a major reason why we learn, especially babies, is to reduce uncertainty. Indeed, there's now, I apologize for all the people who might be on this call whose citations should be, I actually have no idea who's here, I can't see, but more citations are merited. There's just a lot of really beautiful literature that is, to me, part of what's so fun about all this interest in active learning is after a few decades of everyone sort of going very anti-Piaget. This was an argument that Piaget made, which is that infants are, in fact, little scientists who are trying to understand their world by testing hypotheses. Um, that said, there's been relatively little work on language learning, and from the sort of active learning perspective, there's starting to be more. And in fact, most of the citations that I have here were actually are from very recent studies. So when he was a graduate student in my lab, Martin Zetterston, who's now an assistant professor at UCSD, Martin and I got really interested in this idea that uncertainty reduction might influence active learning during language learning tasks. That is, we wanted to test the hypothesis that uncertainty is a motivating factor, leading infants to engage in more active sampling during language learning. And so in our first study, what Martin did was to give little kids, they're 3 to 8 year olds, a really simple word learning task on an iPad, um, where we're going to manipulate uncertainty during the training part that we control. And then they're going to get to choose what they want to learn next. And we can look at their choices as a way to figure out if if they're trying to reduce uncertainty, if they are trying to figure out what the heck is going on here. So here's how the study worked. Um, it is at some level a cross-situational word learning task, just like those that Chen and Linda Smith and their colleagues have pioneered and developed over the past couple of decades. So on some trials, oh, the task here, it's a tablet game. Kids are told that there's an astronaut here, I think his name was Teddy, and he's trying to learn the names of a bunch of aliens. And so some trials, Teddy sees two aliens and hears two novel words. So Teddy might see this blue guy and this yellow guy and hear Cebu, Tibble. This is an ambiguous trial. There's no way to know which guy is the Cebu and which guy is the Tibble. On other trials, Teddy is going to see a novel object and a familiar object like a dog, and Teddy will hear dog biffer. This is an unambiguous trial because based on mutual exclusivity, the child should know for sure that biffer refers to the thing that is not the dog. And we go on like this. We do not disambiguate the ambiguous trials. So they're going to see Cebu and Tibble paired again, and dog and biffer paired again. And across exposure, some trials, some words remain ambiguous. So it never becomes clarified through cross-situational learning what Cebu means. But it is very clear what biffer means. After this exposure, they get to play the game where they get to touch the alien they want to learn about next and hear it labeled. And there's a lot of interesting data in this paper, but the short version is that children sample the objects with unambiguous labels. Excuse me, they sample the objects with ambiguous labels more than the unambiguous labels. That is, when they have a chance to choose, they're more likely to try to pick the yellow guy or this blue guy than this pink guy, where they know the label. And we saw a really large age effect as well, where 3-year-olds were pretty much not showing this pattern, and the older kids were very strongly showing this pattern of sampling the ambiguous items. So this does suggest that uncertainty is motivating sampling, at least in this age group. So what about babies? Do infants sample in language tasks based on uncertainty? How can we find out? Well, one way to find out is to let them choose what to learn about. And so, again, we're going to use infant-controlled eye tracking, but here in a very different way. We're going to give babies exposure to a distribution of ambiguous words, and then we're going to let them self-administer stimuli in a lab-based task. Okay, so this study was part of Martin's dissertation, and let me just walk you through the basic design. So this was 18-month-old infants. During exposure, we're going to manipulate the ambiguity of label object pairings. This is not infant controlled. I'll show you what I mean by manipulate ambiguity. Then they enter a sampling phase where they get to select which objects are going to be labeled based on their own eye gaze. So basically whatever they look at, it lights up and they hear it get labeled. So we could then ask whether this manipulation of ambiguity affects which objects the babies choose to sample. So we have consistently labeled objects during this exposure phase that infants don't control. So this toilet brush looking thing is always called Toma. And then we have inconsistently labeled objects like this mop-looking thing. Sometimes is called Nupi, sometimes is called Kita, sometimes is called Limu, and sometimes is called Guffy. So there's a lot more uncertainty. There should be a lot more uncertainty about the mop-like thing's name than the toilet brush-like thing's name. So after this exposure phase, where we have two objects that are always labeled consistently across different trials and two that are labeled inconsistently, infants enter the sampling phase where they're controlling what happens next. And the question of interest is what they pick. We hypothesize that if infants seek to resolve uncertainty, they should select the inconsistently labeled objects more than the consistently labeled objects. And I should note that during the sampling phase, every object has one and only one name to try to make sure that their choice of sampling isn't because of something being more interesting during sampling itself. So here's how I'll walk you through the trial design and then I'll show you a video of a baby doing the task. So at the beginning of a test trial, they're going to see these four objects on the screen. They're in grayscale. And now the gaze contingent looking phase begins. And depending on where the baby fixates, something will light up, like this mop-like thing. If they're looking at that, they're going to hear Noopy, Noopy, Noopy until they look at something else. And then that thing will light up, Toma, Toma, Toma. This goes on for 20 seconds. So babies are working the screen here like a little video game for 20 seconds. And there are two test trials. So let me show you a video of a baby doing this task.
Noopy, 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 Manu, Manu, Noopy, Toma, Bevo, Bevo, Manu, 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 Noopy, Noopy, Noopy.
Cool, eh? Can't see any of you, but hopefully you're nodding. I think it's really neat to kind of get inside the heads of these kids. Okay, so again, we're interested in their looking time to these objects that were labeled consistently during training versus objects that were labeled inconsistently. And we hypothesize that if infants are trying to reduce uncertainty, they should select the inconsistently labeled objects more than the consistently labeled objects during this test period. And that is in fact what we observed. So we saw greater looking at the inconsistently labeled objects. However, this is the individual data. There's a lot going on here. As Martin finished the study, the pandemic hit. We could not run infant-controlled eye gaze tasks online. And so there are a lot of different controls that one would need to really nail down exactly what's going on here. But I think it's really exciting to think about being able to at least measure infants' so what's driving infant behavior by manipulating the structure of their environments in these sorts of tasks, as artificial as they may be. So again, the current research framework that is motivating my thinking of myself and folks around me in my lab is that part of what's going on here is that infants are flooded with information. They're trying to process it. They're trying to encode the information that they encounter in their environment. And to do so, they're going to try to represent that input in ways that are going to maximize efficient processing. They're going to try to reduce entropy and find units, find predictable patterns, find chunks, reduce uncertainty, learn from prediction error, really doing anything they can to make the input more manageable, more processable. Um, Statistical regularities are just one contributor to this process. There's obviously tons of other information that infants are using to try to reduce entropy, to try to reduce uncertainty in their environments. But statistical regularities are probably one of the, I would argue, likely to be one of the more important processes because you don't need to know a lot to use them. You don't need to know the meanings of the words to figure out which words are going together. And you don't need a lot of complex social information to use this sort of stuff. And so it may be part of what's helping to get babies enough processing of language, enough encoding of language to then be able to really fruitfully take advantage of their social worlds. I'd like to end by talking a little bit about implications for atypical development. That's another strong interest of mine. My lab at the University of Wisconsin is sited at the Waisman Center, which is a center for research on developmental disabilities. And so I've had the privilege of collaborating with my colleagues in communication sciences and disorders to study children of very diverse developmental trajectories. And given the important role of prediction and language input, and in language processing more generally, we became very interested in thinking about the role of prediction in autism. And there's this really beautiful paper that Pavan Sinha wrote about, and his colleagues wrote about 10 years ago. And one of the arguments they make in this paper is that it's not that prediction in itself is necessarily challenged in autistic individuals. They argue that what's different is how information is weighted and suggest that for autistic people, for the autistic phenotype, the data on which predictions are based is perhaps different than for neurotypical people. And they suggest a kind of hyperplasticity, namely that what's just happened is upweighted relative to earlier experience. So the sort of base rates, the sort of overall probabilities in the world may be less relevant to you than what just happened if you happen to be autistic. Um, what's interesting about this for language and just in general, really, as it means that if you are living in an environment that's very stable, where things are generally more or less the same, then you actually wouldn't expect to see very large difference in predictive behavior between an autistic individual and a holistic or neurotypical individual. And in fact, when we look at the statistical learning literature, if you look at basic statistical learning, like the Golabu, Pabigu, Tutibu kinds of studies, autistic people actually tend to do very similarly, if not exactly the same, possibly equivalently, maybe better, to neurotypical people. And that's a whole other talk I could give, which I won't give now. And so with my colleague Susan Ellis Weismer, we decided we would try to understand whether we could observe hyperplasticity in predictive language processing in autistic toddlers. And so we had a grant to do this. I'm just going to tell you about one study. This work was done with Janine Matthews Scott and Catherine Prescott, along with Susan and myself. And what we wanted to do in this study, it's like the simplest predictive behavior task you can possibly imagine. What we wanted to do is to trade off cumulative probability, so the probability that two events co-occur over time, versus what just happened, and see whether we would observe any differences between our autistic toddlers and our neurotypical toddlers. So let me tell you how this task worked. The ages of these kids, the autistic kids their mean age was 31 months. The neurotypical kids, their mean age was 21 months because we were matching them on language. And so when we match on language, we often have autistic groups that are slightly older than neurotypical groups. So in the first block of this task, it's based on other tasks that Alexa Romberg and I have done, that Tracy Reuter and Casey Williams have done. There's rewards on either side of the screen, and the speaker gender predicts the award, the side of the reward. If it's a male speaker, something happens on the left. If it's a female speaker, something happens on the right. So there's a block of trials that look like that. I think there are 12 trials. Simple. Then, block two, we switch the contingencies. Now, if the male was predicting the left side and the female voice was predicting the right side, we flip it, and now the female voice is predicting the left side. And so let me just explain a little bit more about how this works. Sorry, they were matched on cognitive skills, not language skills in this particular study. So at the beginning of every trial, there's a looming circle, and then they hear a female voice or a male voice that says either, look at that, or look at that. And then depending on which voice they heard, either a monkey starts to jump around or a bunny starts to jump around. So this, I'll show you a video of the task. I don't know that I have audio, but I can do male and female voices, so I'll do the audio. Let's see if I can get this to go. Look at that. Look at that. Look at that. You got the idea. And what we're interested in here is anticipatory looking. So we're interested in whether the child starts to look in the correct location before the object appears. We were interested in their predictive eye movements or their anticipatory eye movements. And so here's the logic. If they're making, and we're now looking just at the second block after we've switched the contingencies. If kids are making predictions based on recent evidence, the new contingencies, then they should have really relatively low switch costs. However much learning they had done at the end of the first block, they should relearn really quickly because they're focused on what just happened and not the sort of overall probabilities. However, if predictions are based on cumulative evidence, the probability of a male voice and the monkey over the course of the whole experiment, switch costs should be high. It should actually be quite hard to relearn this task. What did we find? Well, we found that for the neurotypical kids, they actually did really poorly on the second block. They showed a lot of difficulty relearning this incredibly simple pairing. We saw it's like doing a Wisconsin card sort. They seem to perseverate on the old pair. The autistic kids, they learn the new sequence just like that. They learn the new contingencies almost like they'd never experienced the first block. And so we think that this is tentative evidence in support of Pavan Sinha's hyperplasticity hypothesis, namely that there are differences in how autistic and neurotypical folks might be generating predictions, but it's not necessarily about whether they can use predictions. It's about the nature of the data that they're using to generate predictions. Okay, so today I've talked about how infants track regularities in the service of efficient language learning and processing. I've talked about ways in which they might exploit predictable structure. I've talked about how they may detect and detect uncertainty and act to reduce it, and suggested that thinking about language processing through the lens of statistical learning may help us to understand potentially what might be going on in different kinds of developmental trajectories. Our studies and those of many others suggest that rather than being little sponges, infants are actively engaged in seeking out information and structure in their world. This affords some of the extraordinary accomplishments that we observe in language development as babies learn to make sense of the sounds and signs in their environment and in so many other domains. And so I just want to end by thanking all the folks who did all this work, largely not me, the incredible graduate students, postdocs, research staff, and undergraduate students that I've had the privilege to work with, my fantastic collaborators, the federal government of the United States for decades of funding. Thank you, and please, I'm not going to go there. And most importantly, the many thousands of families that have participated. And I'll leave you with my favorite slide. These are my lab's grandbabies. So these are the children of my postdocs, grad students, and undergrads. I think I need to update this slide. It's a little old, but it's always really fun to just get to think about the generativity of science. So with that, I will stop and take questions.